topic is random forest in Python, and so that's going to be broken down into 4 basic sections. First, a little bit of basic background about the model and how it's implemented. A couple of explanatory examples. I'm going to talk a little bit about random forests versus neural nets because neural nets are a very popular topic in model choice. So a bit of exploration as to why you might choose one or the other. And then end off with an example sort of toy AI using random forests. So it's an ensemble machine learning model, which basically means that it's an aggregation of a bunch of simpler models, in this case decision trees. So the individual trees are formed by branching on features in a data set, and a random forest is an aggregation of these decision tree models. So the decision trees, as mentioned, branch on each of the features in order to create a partition of the data. So for each bin in that partition, i.e. a leaf in the tree, you can assign a output value which will be corresponding to each of the inputs that fall into that bin. So 2 major types of trees. First, classification trees. Your output is categorical, and so each branch of the tree formed by a particular set of feature values leads to a different particular output value. So as an example, if you're building a decision tree to show the prisoner's dilemma game, your 2 features are whether or not the 2 prisoners cooperate. And so based on those 4 different possible outcomes in the space, the tree has 4 different leaves and a different set of payoffs for each of those different configurations. Regression tree, you are again trying to partition the output space, but in this case the output is continuous. And so the way that you assign the continuous value at these leaves is to take the mean of the values assigned to a particular bin. So just for a very simple example, absolute value of x from -10 to 10, you only have 3 features in this case, which will give you 4 branches, which partition the output into 4 possible ranges, and so you'd have a different output value for each of those ranges. It's fairly clear to see that the finer you make the partition, i.e. the more features you have, and the deeper the tree, the closer you can get to approximating an actual continuous output. So it's clear that the order of the branches in the tree matters. It's less transparent how the path to each leaf is constructed. And so in practice, this happens according to an approach called entropy minimization, in which you, for each feature, minimize the entropy or maximize the information gain and choose the feature to branch on which maximizes the information gain. I've left out the formula because it's not particularly intuitive if you're not familiar with information science, but there is some pretty simple intuition to understand how that branching process occurs. So the problem is basically, given a set of features, how do you partition the output space as finely as possible, as quickly as possible? And for useful analogy, I would point you to the game Guess Who. So in the game Guess Who, for those of you that don't know, players try to identify the opposing player's character from a preset list of characters. And to do that, individuals take turns asking yes or no questions to expose features about the character. So, low information gain. The way that people typically play this game is to ask questions like whether the character wears glasses or has white hair, and these represent low information gain features. So generally, I ask, does a character wear glasses? The answer is no. I've eliminated maybe 3 possibilities, and I haven't gotten very far. A higher information gain feature will partition the data as evenly as possible, regardless of the answer. So in the case of a yes or no question, the best you could do is to partition the data in half with each question. So a high information gain question would be something to the effect of, is your character Bob or Ted or Jen, and then list half the characters, and then you have a yes or no question that guarantees to eliminate half of all your possibilities. So in this way, you've eliminated half the possibilities, and in general, you can identify the target character in log n guesses. So that's decision trees, and now we can move into making a forest from these decision trees. So overfitting is a well-known pitfall for these decision trees. This should be fairly clear to see from the Guess Who example. Building a feature that's like, is your character in this half of all characters, is very overfitty. And if the data changes at all, it's likely to underperform a more general feature like the kind of questions that you would generally ask, like, you know, white hair. And so the way that we overcome this pitfall is by building an ensemble model from these decision trees. And we do this with a procedure called bagging. So just to make it explicit, what an ensemble model is a model that is made by aggregating other models. So in our case, averaging a bunch of decision trees is going to result in predictions that are still unbiased like the individual trees, but because it's an aggregation of a bunch of other models, the variance of our estimator will go down. So the bagging procedure is for some number of trees, t, and a predetermined depth, we select a subset of the data, usually 2/3. You can tune that parameter based on the requirements of your problem. You train a decision tree using a subset of the features on that subset of the data. Again, the square root of the number of features is the convention, but you can tune that based on your particular problem. So if you think that your features have complex interaction, then you might want to have a deeper tree because you would want the decision trees to capture the interaction of those features. But if you think your features are, you know, largely independent, then having very deep decision trees doesn't make a lot of sense. So you train the individual trees like that, and then they can be aggregated. So in the case of a classification problem, we can use the mode of the individual trees to form our aggregate prediction. In the case of a regression problem, we can use the mean of the trees, and so that way, you know, we can use the individual models that we've trained to get either categorical or regression output, and that process happens completely independently from how the trees are trained. So this helps us avoid overfitting. The individual trees, it's hard to overfit them if you're only using a subset of the available information. And by building the random forest, we can build sort of a stronger aggregation model from these weaker models, in that the individual decision trees, while unbiased, are weakly predictive. And so this aggregation reduces the variance of the subset of trees. So strong suits of random forests. The reason that they're sort of a generally very effective tool is that they're robust to lots of different kinds of data. So nonlinear, non-monotonic functions. If your data is unscaled, data with missing values, poorly chosen features. So what this all sort of combines to is if you don't have a lot of preconceived notions about your data set, then random forests tend to be a very good sort of first pass model to try. So a couple of examples. Nonlinear functions. So we'll start with a function that's x times the sine of x plus some random value. It's a pretty simple function, but a lot of models will have trouble sort of capturing that nonlinear, non-monotonic behavior. Certainly something like simple regression as like a easy out-of-the-box thing to try will fail miserably here unless you have some very clever feature extraction. So simple code to generate the example. A generate data function which will map x value to the output that we just discussed. So x, y, we generate the data, and then I'm taking a random forest regressor from scikit-learn. There's absolutely zero parameter tuning here. It's just straight out of the box application of the regressor model. And the output we get is this. So that yellow line being traced through the data is the model prediction, and the blue dots are actual data points. Without any kind of tuning, we're capturing the sort of complex shape of the function fairly easily. And while there is a bit of noise in the function, it still sort of captures the basic behavior of the function. Yeah. So the next example I wanted to look at is unscaled features. In this example, we'll just take points across the 4 quadrants of the Cartesian plane, so like northeast, northwest, southeast, and southwest. But the one tricky piece here is that we're going to use weird ranges. So the x values will cover just negative 0.1 to 1, while the y values will go from negative 5,000 to 5,000. And so our 2 axes are of pretty different scale here. Again, very simple example, function to classify the quadrant of a given point, and then x and y are just randomly simulated pairs. And then we take a random forest classifier and fit the coordinates to the quadrant. Again, there's absolutely no parameter tuning here. This is just naive out of the box. And this is the output that you get from that. Basically exactly what you would hope for. All of the points are classified correctly despite the very awkward ranges. And for those of you that were thinking in the last example that our regression model was overfitting to a lot of noise, and that a model like Neighbors or SVM would fit this more smoothly. That might be true, but in an example like this, models like that are sort of sensitive to the scale of features are going to fail pretty miserably. So for example, k-nearest neighbors out of the box will give you this. So we'll capture the north and south pieces, but completely miss the more fine x-axis. And if you do this with support vector machines, you'll again get these exact same results. So models like that would require sort of more tuning or feature extraction. So forests versus neural nets. Neural nets are very popular and they work very well. Why not just use them for everything? Parameter tuning tends to be a lot simpler for forests. So even if you do need to do parameter tuning for examples that are more complicated than the sort of toy examples that I've just run through, there are sort of clear conventions around choosing parameters, and there's pretty clear intuition around like how you would choose things. So, deciding the depth of a tree depends on the complexity of feature interaction, or like choosing the number of trees depends on like a trade-off of training time versus performance. There's very sort of clear, easy intuition for how you choose these parameters. Whereas in the case of a neural network, saying, I want my network to have 4 layers with this particular network topology and X like connectivity and weights, the intuition behind how you choose those things is not particularly obvious. There's a more robust body of academic literature around forests just for the reason that they've sort of been around longer, which makes the internal workings easier to understand, which again goes to this issue of being able to make sort of reasonable judgments about tuning the models. Generally simpler to implement. The examples that I just did with the random forests, obviously those are uniquely simple cases, but it's just model.fit, model.predict. There's not a whole lot else to it. Whereas even with sort of simple wrappers like Keras, there's still a fair amount of configuration around creating the individual layers and making decisions about the topology of the layers. Scaling. So random forests are inherently parallelizable and extremely well supported for distributed deployment. So through MLlib, which is included in Spark, you can do a distributed random forest very easily. The actual syntax winds up being basically the same as through scikit-learn. And you can do that for arbitrarily large data sets because the data is partitioned over a cluster. And so given that each decision tree is pulling a subset of the data, your data will be co-located with the tree it's trained on. And so you're just aggregating the trees from the cluster. Doing that kind of distributed deployment of a neural net is much less straightforward. So the last thing that I want to do is a simple AI example with random forests. And so the problem that we're going to run through is basically building a simple array search. So given an array of sorted numbers, we'd like to find a target value as quickly as possible. The standard example here, or the standard approach, would be binary search. But in our case, we're going to say that the random values are exponentially distributed. And so our challenge is to use this information to build a search algorithm that's faster than binary search. So the approach we're going to take is to create a bunch of sample searches. So random search, just randomly picking values. Linear search, going in whatever direction, one by one until we find our value. And binary search, the sort of prescribed algorithm. And at each step, we're going to create an observation. The observation will be our current location, a floor on the range that we know, a ceiling on the range that we know, and a ratio of the value at our current index over the target value that we're looking for, which presumably encodes some information about how far away our target value is according to the underlying distribution of the values. So I am not going to go through all the code to actually generate this. You can go to that repo and find everything if you want to actually look through the internals. This basically captures the gist of it. So you have a search simulation class which will take a training size and an array size. In this case, the array size will just be 100. And it'll generate a set of states and a set of prescribed deltas. So then we can build a random forest classifier that fits the states to a prescribed delta, and then build a search class that updates its location based on its prediction of the appropriate delta at its current location and given its current state. So the results of this, of our 4 searches, random search at the far left, then linear, then binary, and then AI search slightly outperforming that. And then just to dive into a bit, AI search versus binary. There we go. So binary search is here in the blue on the left, and AI search is the red one. So you can see at the extreme end, there are a couple of cases in which AI search underperforms binary, and so you, in a sort of production application, would probably want to do some deeper dive on like these tail examples to figure out sort of why it's getting confused in that case. But for the most part, at almost every quantile, the AI search is fairly substantially outperforming binary. Yeah, that's what I got.
Okay, so we'll now take some questions. Yep.
Hi.
In your day-to-day work, why do you choose random forest, for instance, over other methods? I
Um,
mean,
yeah, as I mentioned, I think the. Oh, yeah, sorry. The question is why you would choose random forests over other methods. And I think the reason that I like random forests is that they are very robust to a lot of different types of data. So certainly if you have sort of preconceived notions about your data set that suggest a specific model, by all means do that. But random forests will tend to give you at least a reasonable answer, regardless of your data, unless you're making some pretty wild choices. So it's a very good out of the box, I'm trying to just build something reasonable as quickly as possible kind of approach.
so during your work at Bloomberg, can you give us an example of how you would use random forests, just briefly, to solve a problem, a classification one, for instance?
Um, it's not actually super connected to the work that I do at Bloomberg. I actually do like data pipeline kind of stuff, so it's a lot more like distributed systems, Spark data ingestion kind of stuff. Sorry, I realize that's not a very helpful answer.
Can you talk a bit about feature importance and as an aid to eliminating irrelevant features?
Sorry, could you speak up a
Yeah.
bit about feature?
Feature importance.
Okay, yeah.
Yeah, so as a way to eliminate irrelevant parameters.
Yeah, so I mean, I guess in general, like in the case of random forests, if you have like a lot of irrelevant features, if you're training a lot of the decision trees based on those features, you could wind up with an erroneous model. So I guess one way to sort of do feature extraction is if you're training on sort of shallower trees, then shallower trees with a larger subset of the features, so each decision tree has the sort of full pool to pull from, then your individual decision trees will tend to pick up on the features that actually matter because they have the full sort of option, the full set of features to choose from while you're doing the entropy minimization procedure. So that is sort of a way in which you can sort of quickly get a sense of the features that matter, and if you do think you have sort of features that need to be pruned, that would be sort of a way to identify that set. I don't know if I'm answering the question. All right.
How do current implementations of random forests deal with categorical features?
Yeah, I mean, I don't. Sorry. So the question is basically how does current implementations of random forests deal with categorical features? I wouldn't comment necessarily on like specific implementations, but as a model, random forests are pretty well set up to deal with categorical data because like the underlying models are trees. So if I have categorical features, then like my branching is on each possible output value of an underlying feature. And so if I have, just all categorical data to make an extreme case, then like there's really no need for like any kind of continuous approximation. It's all just binning according to those categories.
Do you have to specify when you're running the random forest? These are categorical variables, these are continuous variables, or does it pick it up? Like how would it understand which is which?
I would say in general, it kind of depends on the implementation or library that you're using. But if you do have categorical data as a guarantee against having any issues there, you can do one-hot encoding. So basically, like for each categorical value, you extract that into features that say, instead of, so a categorical feature that can have like values A, B, and C, I extract new features that say A equals 1, B equals 1, C equals 1, and then I have numerical values, and so I don't have to worry about that issue. Hmm.
But can you explain a bit on how?
So individual trees, I can build the tree without if I have individual values that have like missing columns. Um, the subtrees can be trained on a subset of features that don't include that particular column.
Could you compare the random forest techniques with other techniques in terms of training speeds?
So the question is compare random forests to other techniques in terms of training speed. There's obviously a pretty wide universe of other techniques, so that's like a pretty difficult question to answer succinctly.
Perhaps a neural network.
Yeah, so in general, I think, again, depends on the architecture of the neural net, but like in very extreme cases, you can get, I think, sort of faster training performance with a random forest, particularly if you do like some kind of parallel or distributed approach, because the individual trees are pretty amenable to being done in parallel than aggregated. Whereas, in the case of a neural network, there's a lot of reaggregation that has to happen. So it's not necessarily easy to train the net with, all of your data being in different places. On a single machine, the amount of training time, it very much is a question of the architecture of the net.